Hello everyone, thank you so much for joining us in this ICRP webinar. I'm Yeon Soo-yeon from Yonsei University, Korea. I'm a member of ICRP Committee 2 and a member of ICRP Task Group 103. So I'd like to introduce the new the ICRP, the Pediatric Mesh Phantoms, particularly focusing on the background and motivation. So as you know, the equivalent dose and ultimately the effective dose are special dose quantity defined by the ICRP for radiological protection purpose. For practical implementation of radiological protection, effective dose especially not defined each individual, but defined for sex averaged the reference person representing the whole populations. Also, these protection quantities are not directly measurable. Therefore, the ICRP has provided the dose coefficient for external and internal exposures to convert the measurable quantity to the protection quantities. So these dose coefficients have been calculated by performing the Monte Carlo simulations with the computational phantom for the idealized exposure scenarios. So before the current at the ICRP 103 recommendation, actually ICRP did not specify the particular phantom. And in fact, the various mathematical phantom had been used. In ICRP 103 recommendation, the ICRP first specifies the reference phantoms considered as a reference person for the calculation of protection quantities. So this slide shows the adult, male and female, the reference computational phantoms, the adopted, the following the current ICRP recommendations. The adult reference phantoms were released by ICRP publication 110 in 2009. So these reference phantoms are voxel models constructed from the CT images of the real patients. So therefore, the anatomically much more realistic than the old type mathematical phantoms, which are previously used for the ICRP dose coefficient calculations. In 2020, the pediatric male and female, the voxel type, the reference phantoms were also released by the ICRP publication 143. So this pediatric phantom covered the 5 different ages: newborn, 1 year, 5 year, 10 year, and 15 years. Although these reference voxel phantom have been beneficially used for the calculation of the reference dose coefficient for the current ICRP 103 recommendations, they still have some limitations due to the voxel resolution limited to the millimeters. For example, a thin structure such as the skin is not continuously represented because the voxel size are greater than the skin thickness, about 1 millimeter. Even the pediatric phantom have smaller voxel size but still show the same problem in the skin. The same problem can be also found in the hollow organs, not only for the adult, but also for the children. And another example is the eye range, which is very small and also thin structure, and therefore they cannot be correctly defined in the voxel phantom. So as you can see, the eye range of the adult male phantoms are directly exposed to the air. So this anatomical problem can result in significant overestimation in range dose calculation, especially for weakly penetrating radiation. The 1-year-old phantom also showed the same problem in the eye model. And going back to the skin, there is a much more critical problem in the skin dosimetry using the voxel phantoms. That is, the radiosensitive, the basal cell layer in the skin need to be considered as a target for skin dosimetry, but Such thin layer in micrometer scale cannot be defined in the voxel phantom with the millimeter resolutions. Similarly, the respiratory tract system actually has the 8 to 15 micrometer thick radiosensitive cell layers, which again cannot be defined in the voxel phantoms. As a result, 24 additional stylized models have been used for the SAF calculation in the respiratory tract system together with reference voxel phantoms. Even in the elementary tract system, the 42 additional stylized models have been used for SAF calculation together with the reference phantoms. The other limitations are listed here. Among them, particularly, I'd like to stress that the reference organ mass, the reference phantoms are matched to the reference organ mass exclusive of the blood content. So that's why the organs are smaller than usual by 3 to 20%. And meanwhile, the phantom technology in the world has been advanced via the second generation of the voxel phantoms toward the first generation of the phantom based on tetrahedral mesh in order to represent the human anatomy more realistic and precise. So at the beginning, the human body is very simplified, such as box, cylinder, and sphere in those calculations. We consider the first generation of the computational phantoms is stylized phantoms, which also called mathematical phantoms. These stylized phantoms, the first define the specific organs using the mathematical equation, so we can do the organ specific those calculations. However, as you can see, it is not really realistic. From 1980s, the voxel phantom, as like the current ICRP reference phantoms, are considered as the generation of the computational phantoms. As I said before, the voxel phantoms are based on tomographic images of human anatomy and therefore much more realistic than the previous stylized phantoms. However, due to the limited voxel resolution, mostly the millimeter scale, the voxel phantoms are difficult to define very thin or tiny organs or tissues, such as the micron thick, the radiosensitive target layer, as I mentioned before. And also, the voxel models are not really deformable, and it's difficult to deform the posture or change the organ shape, and also inevitably represent the stair-stepped boundary of the voxel geometry. So to address the limitation of the voxel phantoms from 2000 years, the NURBS or the polygon mesh based surface phantoms are considered as third generation. So these surface phantoms show the smooth boundary and also can model very thin and small structures because this surface model is very flexible and even highly deformable, so we can change the geometry as we wish. And however, most of the existing surface phantom unfortunately need to be voxelized for the Monte Carlo dose calculations. So this means that it is going back to the voxel phantom, so we lose the advantages of the surface phantoms. So it should be noted that the pediatric, the reference voxel phantoms were constructed from the voxelized model of the NCI pediatric, the surface phantoms. So in 2011, the Hanyang University research team developed the polygon mesh surface Korean phantom, and also first to show that this polygon phantom can be directly used for the Monte Carlo dose calculations, though without any voxelization process. However, the computation speed the extremely slow when compared to the corresponding the voxel phantom by up to 19 times. In addition, the sub-organ density variation that cannot be described in the surface phantom. So now I would like to stress that the first generation of the computational phantom, which is the tetrahedral mesh phantom. In 2014, the Hanyang University research team published the paper where the tetrahedral mesh Korean phantom was first introduced. So these tetrahedral mesh phantoms were constructed by converting the polygon mesh phantom into the tetrahedral mesh by filling tetrahedrons fully inside the volume of the polygon mesh, so which is called tetrahedralization. As a result, we can fully maintain all the advantages of the surface phantom because we don't change any geometry of the surface phantoms. Instead, the tetrahedral mesh phantom can dramatically accelerate the Monte Carlo dose calculation computation speed when compared to the polygon mesh phantom by up to 250 times. This means that the computation speed of the tetrahedral mesh phantom is generally comparable or even faster than the voxel phantom for some cases. In addition, the sub-organ density variations can be also represented in the tetrahedral mesh phantom. So, tetrahedral mesh phantom, considered as the first generation of the computational phantom that provide the most superior when compared to the previous the voxel and the surface phantoms. So acknowledging the limitations of the current voxel type, the reference phantoms, and also the cutting edge, the phantom technology with the tetrahedral mesh, in 2013, the Committee 2 meeting decided to convert the voxel type, the reference phantoms, into the high quality mesh format. So these new mesh type reference phantoms will replace the current the voxel phantoms from the next ICRP general recommendations. So to implement this project, the task group 103 was established in 2016. So this is the current membership of the task group 103, which is led by the professor, the Chanyoung Kim at Hanyang University, Korea. So the first achievement of the task group 103 is the adult mesh type reference computational phantoms, which were released in ICRP publication 145 in 2020. The second achievement is the pediatric mesh type reference computational phantoms, released in publication 156. So now we are introducing these publications through this webinar today. So there are main points. These are main points of the publication 156. The first, the ICRP 156, the pediatric mesh phantoms, are counterpart of the ICRP 143, the pediatric voxel phantoms. The second, the pediatric mesh phantoms were constructed basically by converting ICRP 143 voxel phantoms into the high quality mesh format, but overcome all the limitations of the voxel geometry. So third, The pediatric mesh phantom include all the necessary source and target tissues defined by the ICRP dosimetry system, even including the micrometer scale, thickness, the source, and target layers. First, the mesh type pediatric reference phantom can provide the dose coefficient, especially different from the boxer phantoms for the anatomically improved organs and tissues, and also the weakly penetrating radiation, such as the electron and the photon lower than 50 kV. And lastly, the pediatric mesh phantoms will be used for all the calculation of the reference dose coefficient for following the next set of the ICRP, the general recommendations. So these are the main context and the annex of the ICRP publication 156, so which will be mostly explained by the Dr. Chansa Choi following my presentations. And supplementary material of the phantom data can be freely downloaded in this ICRP website. The Dr. Bang Sin will comprehensively explain later how to download and use the pediatric mesh phantom in more detail. Thank you very much. Hopefully from my presentation, you may understand why we developed the new mesh type pediatric reference phantoms. Then I will hand over to the next speaker, Dr. Chance Choi.
Hello, I am Chance from the University of Florida, and I'm also a member of ICRP Test Group 103. It's a great honor to have a talk in today's ICRP webinar. Just before me, Professor Yum provided a detailed overview of background behind the development of pediatric mesh phantoms. So in my talk, I will focus on their development procedure and their significance in the dosimetric applications. Let me briefly introduce the content of this talk. The structure is almost similar to ICRP publication 156, except for the sections already covered by Professor Young. In the first three sections, I will describe the development procedure of the pediatric mesh phantoms, and in the following three sections, I will highlight their key features, including anatomical and geometric improvement, computational performance, and dosimetric impact. And finally, I will summarize this talk. In the first section, I will explain the process of converting the pediatric voxel phantoms into the mesh format. This process involves two steps, that is, generating mesh replicas that preserve the structures of the original voxel phantoms, and remodeling or modifying some organs with anatomical or dosimetric issues. First, I will talk about how we made the mesh replicas. As Professor Yum explained earlier, the pediatric voxel phantoms were developed from the third generation UFNCI phantoms in nervous and polygonal mesh surfaces through the voxelization process, along with the several organ modifications and additions to become reference ICRP phantoms. The original UFNCI phantoms preserved better anatomical structures from the original 3D images, and they can also be easily converted into the mesh format. For this reason, we used the UFNCI phantoms as the starting point and adjusted them to match the voxel phantoms as the target geometry. This approach allowed us to generate mesh replicas that preserved better anatomical details while keeping consistency with the voxel phantoms. And I will show you the few examples. For the heart, which was originally in the nervous format, we first converted it into the mesh format. The initial mesh quality was poor, so we increased the number of the faces and refined the mesh quality. Then we reduced the number of faces to the reasonable number because too many faces could slow down the Monte Carlo simulation speed. And after that, we adjusted the mass and aligned the shape with the voxel phantoms. Another example is the small intestine. Because of its complex structure, the initial mesh after conversion had significant overlaps and defects, unlike the previous hard case. So we performed additional processing steps to improve the mesh quality and at the same time eliminate these overlaps and defects. Once that was completed, the remaining steps were carried out in the same way as in the previous case. The next example is the cranium, which was already in the polygonal mesh format. In this case, format conversion was not required, but as you can see, it had many mesh defects and was also made of too many faces. So we removed the defect, reduced the number of faces, and then followed the same steps as before. We also applied similar steps to the other organs to convert them into the high-quality mesh format. After completing the conversion of each organ and combining them, we found slight overlaps between some organs. So we carefully adjusted overlapping regions to eliminate all intersections and finally obtained clean, high-quality mesh replicas of the voxel phantoms. This slide shows the generated mesh replicas for 1-year-old male and 15-year-old female as examples. As you can see, the organs were successfully converted into the fine mesh while keeping their original shapes. During the conversion process, we continuously monitored two geometric similarity metrics to validate the quality of the conversion. The first was the dice index, which represents the overlapping volume fraction between two objects, and we kept this value of 0.9 between the pediatric voxel and mesh phantoms. The second was the centroid distance, which measures the distance between the centroids, and we kept this value within 2 millimeters. After generating mesh replicas, we performed remodeling or made modifications to some organs that had anatomical or dosimetric issues. First, we improved the eyes. As you can see, the voxel phantoms do not properly represent eye structures because of their limited resolution. In addition, some parts of lens is exposed outside the eyeball. The lens dose is very important for radiation protection purpose, so for the adult case, this issue was addressed by converting the ICRP 116 adult stylized eye model into the mesh format and placing it in the phantom. But for the pediatric case, such models were not available, so we first developed pediatric stylized eye models for each age group. For this, we selected the 9 anatomical parameters shown in this table, following the adult stylized eye model. After that, we reviewed many literature sources and selected data to use based on the criteria shown below. Finally, we determined the values for each anatomical parameter accordingly. This slide shows the determined values for each age group and each anatomical parameter, along with their corresponding representations. The developed pediatric stylized eye models were then converted into the high-quality mesh format and installed in the phantoms. As you can see, the final models include the fine anatomical structures, including the red-colored thin radiosensitive region in the lens. Next, we improved the teeth. Even though the teeth are not the typical radiosensitive target tissues, they served as an important source region for internal exposures because radionuclides can be deposited or retained on the teeth following the food intake. But in the voxel phantoms, teeth are simplified and do not reflect age-dependent eruption patterns, so we need to improve these models. Also, enamel in the teeth can be used to support EPR or ESR dose reconstruction in emergency exposures, so we decided to include detailed tissues, including enamel, in the teeth. For this, we first reviewed various literature sources to find out which teeth had erupted and which remained unerupted at each age. After that, using the equation shown below, we calculated the mass of each tooth. This table shows the age-specific erupted and unerupted teeth, along with their mass information determined through this process. Next, we determine the density, volume ratio, and thickness of tooth tissues, including enamel, dentin, cementum, and pulp. And then we applied these values to the previously calculated tooth masses to calculate the tooth tissue masses in individual teeth. Based on the determined data, we developed the tooth models and integrated them into the mesh phantoms. For the permanent teeth, we used the models obtained through the micro-CT imaging conducted by the KIST, and for the deciduous teeth, we used the commercially available models created through the molding or 3D scanning. These models were properly combined and used according to each age. And this slide shows the developed tooth models installed in the phantoms. As you can see, these models reflect age-dependent eruption and include the detailed tooth tissues such as cementum, enamel, dentin, and pulp, all realistically defined for each tooth. Next, we also improved the column. Because of the limited resolution of original city images, the column was modeled using the simplified cylindrical shapes in the voxel phantoms. Then the column wall was defined to match the reference wall mass. But the content volume was not based on the reference value, which resulted in underestimated mass or density of the content, and also the inner wall was connected discontinuously. Another issue with the column was the middle part of the transverse column was unnaturally curved downward compared to the actual anatomy. To address these issues, we first developed a stylized column models in the form of smoothly connected truncated cones. Following the method shown in this flowchart, the models were created through numerous iterations to find the truncated cone dimensions that satisfy all region-specific reference masses and lengths for both the wall and content. These models were then converted into the mesh format and implemented into the phantoms. During this process, we also corrected the previously mentioned issue regarding the transverse column paths. Next, we improved the thyroid. The thyroid is a well-known radiosensitive target organ and also key source organ in internal exposures. So to minimize the dosimetric bias, its shape and position need to be typical. It is generally located just below the red dashed line, indicating the boundary between the it region and trachea, but because of individual variation in the original CT images, it was positioned slightly higher or lower. We also confirmed that the isthmus, the front part of the thyroid, was defined thicker than its typical shape. To improve this, we selected 5 anatomical parameters: isthmus height, width, thickness, overlying tissue thickness, and anatomical location. Then we collected and selected data from the various literature sources to determine the values for isthmus dimensions, overlying tissue thickness, and anatomical location. Only for isthmus height and width from 1 year to 15 years, no data were available, so we derived these values by linearly interpolating between the newborn and adult data. Based on the determined data, we adjusted the shape and position of thyroid in the mesh phantoms. Compared to the previous voxel phantoms, the isthmus became thinner and the thyroid was placed in the typical position across all ages. In addition, many other organs in the pediatric mesh phantoms were improved. Here you can see the improved cranium of the mesh phantoms, which reflects the actual size of fontanelles in younger ages, and the spine replaced with the new high-quality models, and hand and foot bones again replaced with the new models. In addition, each region was improved to have a more realistic structure, and lymphatic nodes were newly generated using the dedicated program developed for the adult mesh phantoms, but with the pediatric data applied. And blood in large vessels were remodeled using the modeling techniques, and the muscle was also remodeled. The exterior body contour was also adjusted to be more realistic. In addition to the organs mentioned earlier, improvements were also made to the organs listed here, completing the conversion of pediatric voxel phantoms into the mesh phantoms. In the second step of development, we increased the volume of the developed organs, considering intra-organ blood content. As Professor Yum explained earlier, the voxel phantoms were matched to the ICRP publication 89 reference organ masses, which represent the organ parenchyma excluding the blood content. But in a living person, a significant amount of blood content exists within the organs, and if this is not considered, the organs can be defined smaller than actually they are. And this can lead to significant differences, especially for the internal dosimetry. So just like we did for the adult mesh phantoms, we also account for the blood content in the pediatric mesh phantoms. For this, we first calculated the blood content mass by multiplying the reference total blood mass by the age and organ-specific blood volume fractions reported by Wason and his colleagues. Also, assuming the blood content is uniformly distributed within each organ, the densities and elemental compositions were recalculated considering the mass ratio between the organ parenchyma and blood content based on the simple equations shown here. After determining the organ data, including the blood content, we increased the organ size in the mesh phantoms. To preserve the original organ shapes as much as possible, we use an offset function to uniformly expand the organ surface outward. After applying the offset, some organs can overlap. In such cases, since smaller organs can be more affected by deformation, the larger organs were adjusted to remove the overlaps. This slide shows the pediatric mesh phantoms before and after accounting for the blood content within the organs. Since adjustments were made while preserving original organ shapes as much as possible, they looked almost the same. But the masses of major organs actually increased by more than 20%, and organ distance became closer. This allows the phantoms to better represent the anatomical characteristics of the living person. As a final step of development, we defined the thin micrometer scale radiosensitive target and source regions in the skin, urinary bladder, lavatory and respiratory tract organs. For the skin, radiosensitive target region is located between epidermis and dermis, as well as around the hair follicles. The ICRP assumes this target region is distributed between 50 and 100 micrometers in adults, but no such information has been provided for children. This issue was carefully discussed in our test group and ICRP Committee 2, and we decided to apply the adult range to 15-year-old, but use 40 to 100 micrometers for younger ages, considering the follicle depth is similar, but the epidermis is thinner in children. The skin target region was simply defined at this depth using the previously mentioned offset function, and this slide shows the skin target region defined in the 1-year-old female and 15-year-old male as examples. The urinary bladder also includes the thin target region with age-specific depths provided as shown here. Similar to the skin, this target region was simply defined, and this slide shows the target region defined in the urinary bladder for 10-year-old male phantom as an example. The elementary tract organs include not only the target region but also various source regions. The depths for each region are provided in ICRP publication 100 as shown here. Except for the villi, one of the source regions in the small intestine, it is assumed the adult depth can be applied to the children. Based on these depths, we simply define the most target and source regions like the previous cases. Here you can see the target and source regions defined in the esophagus, stomach, small intestine, and colon. For the oral cavity, the target and source regions were defined with additional process because of relatively complex structure. This figure shows sagittal view of oral cavity stylized model. The red line at the top represents the target region on the roof of the mouth, and the red line at the bottom indicates the target region within the tongue, and the green area represents the food content on the tongue surface, considered as the source region. As in the adult phantoms, the current phantoms do not include the dedicated space for the food content, so the tongue was divided into upper and lower part, and the upper part can be used as a food content when it is needed. Then the target regions in the roof of the mouth and within the tongue were defined using the offset function. Also, this figure shows transverse view of the stylized model. The white area represents the teeth. Green line is the source region indicating the radionuclides deposited on the tooth surfaces, and the red line shows the target region in the cheeks and lips. Based on the exposed region of previously developed tooth models, we applied various modeling techniques to define the source and target regions at the same depth as in the stylized model. And this slide shows the target and source regions defined in the oral cavity through this process. Likewise, the respiratory tract organs also include target and source regions. The depths for each region are provided in ICRP publication 66 as shown here, and it is assumed that the adult depths can be applied to the children. For each region, both target and source regions were simply defined. Here you can see the target and source regions defined in ET1 region, and this slide shows ET2 region. In the case of large BB and small BB regions, which represent the airway generations in the lungs, they were not defined in the voxel phantoms. So we generate them in the pediatric mesh phantoms using the same airway generation program developed for the adult phantoms. For this, we calculated the generation-specific length and radius based on the method described in ICRP publication 66 and used them as an input of the program. Only for the newborn, these values were additionally revised based on the anatomical grounds before the airway generation. And this slide shows generated large BB and small BB regions along with their target and source regions. Since representing these structures in the mesh format requires significant memory, they were developed only in the CSV format. So the files for this are provided as supplementary files, and more detailed explanation about these files will be covered in Dr. Shin's upcoming talk. With the definition of these thin target and source regions, the phantoms are now fully developed. Now let me briefly go over the key features of developed pediatric mesh phantoms. Here are the completed mesh phantoms for the newborn 1-year-old, 5-year-old males and females, and 10-year-old and 15-year-old male and females. In the voxel phantoms, some organs such as breast and muscle were exposed outside the skin, but this issue was fully addressed in the mesh phantoms. Likewise, in the voxel phantoms, the spondiosa was significantly exposed outside the cortical bone, but in the mesh phantoms, it was fully enclosed. This table shows various numerical properties of developed pediatric phantoms. Their height and weight were aligned with ICRP 89 reference values, and organ masses, including blood content, were matched within 0.1% of their target values. Like the adult phantoms, each pediatric phantom consists of approximately 6 to 8 million tetrahedrons. Although the phantoms were initially developed in the polygonal mesh format, they were later converted into the tetrahedral mesh format for better Monte Carlo code comparability and performance. So the final product of this work are the tetrahedral mesh phantoms, but we also provide the polygonal mesh versions for the users who need the further modifications or the deformations. Next, we evaluated and compared the computational performance of the pediatric mesh and voxel phantoms in the Monte Carlo code. From this evaluation, we selected 5-year-old male phantoms and transported 10 to the 5 primary particles under the LLAT geometry. We used 3 Monte Carlo codes, GM4, FIT, and MCP6. The following slides show the computer specifications and the transport environment used for each code. We basically used the default settings and only made a few adjustments to ensure the consistency between the codes, and I will skip the detailed explanation on this. The computational performance can be explained by 2 factors, memory requirement and computation speed. Regarding the memory requirement, we confirmed the FIT code requires smaller memory for implementation of the mesh phantom. In other codes, the memory requirement is larger than the voxel phantom. But this is still much smaller than 16 GB for all codes, which is usually equipped in the personal computer or laptop these days, so it doesn't have significant impact on the simulation. And the graphs below compare the computation speed for several particle types, photons, electrons, and neutrons. A value above unity means the mesh phantom is faster, otherwise it's the voxel phantom. From this result, we confirmed that the FIT code provides faster or comparable speed for the mesh phantom across all particle types. And the GM4 code showed comparable speed, sometimes faster, sometimes slower, depending on the energy. Only in MCP6 was mesh phantom slower, mainly because MCP has limited optimization for the tetrahedral mesh geometry, even though it supports the penta or hexahedral mesh geometry as well. Considering the highly detailed structure of the mesh phantom compared to the voxel phantoms, we believe these are very encouraging results. Next, let's take a look at the dosimetric impact of developed pediatric mesh phantoms. For this, we performed Monte Carlo simulations using the GM4 code, and we calculated organ and effective dose coefficients for external exposures and compared them with the results from the voxel phantoms. We also calculated specific observed fractions, SAFs, for internal exposures, and then compared them with the results from the voxel phantoms as well as the stylized models in cases where the voxel phantoms cannot be used. Let's take a look at the external exposures. This slide shows the readable Merrill dose coefficient for photons under AP, PA, and ISO irradiation geometries. The markers indicate the values for the mesh phantoms, and the solid lines indicate the values for the voxel phantoms. Also, the same color represents the same age. From this result, we can see that the mesh and voxel phantoms showed very good agreement across most energies. But at the lowest energy considered, 10 kV, large differences were observed, with the result differing by up to a factor of 9. This is because, unlike the voxel phantoms, the spondosa is fully enclosed by high-density cortical bone in the mesh phantoms. For electrons, the shielding effect of cortical bone became even more pronounced. As a result, significant differences were observed wide range of energies, with the maximum difference reaching up to 55 times at low energies. Next is the skin dose coefficient for photons. Like in the previous cases, the result from the mesh and voxel phantoms agreed very well across most energies. Only except for 10 kV, where we observed the larger differences of up to 1.7 times. This difference is mainly because, unlike the voxel phantoms where the skin dose was calculated for the entire skin, the mesh phantom calculated this value specifically for the thin microscale radiosensitive tissues. For electrons, the use of skin target layer resulted in much greater differences, reaching up to 22,000 times at low energies. Next are the effective dose coefficients for photons. While some differences were observed in the organ dose at low energies, the effective dose agreed within 10% across most of energy ranges. For electrons, we observed significant differences across a wide range of energy, with the maximum difference reaching up to 22,000 times, which is similar to the skin dose differences. This is because the skin dose is a dominant contributor to the effective dose calculation at low energies, even if each tissue weighting factor is very low. Next, let's take a look at internal exposures. This slide shows a photon SAF for the self-irradiation cases, where the source and target organs are the same. The results from the mesh and voxel phantoms generally showed good agreement. But for organs like the liver, where the addition of the blood content significantly increased the mass, relatively large differences were observed because of the differences in the target mass. These differences became even more pronounced in the electron SAFs. This issue in self-irradiation cases was recognized by the ICRP, and the recently released ICRP publication 155, the observed fractions were calculated using the voxel phantoms, but divided by blood-included organ masses in these cases to address this effect. Please note that the differences presented here do not reflect such a correction. This slide shows the photon SAS for crossfire cases where the source and target organs are different. Compared to the previous cases, we observed much larger differences at low energies. These differences are mainly due to the several improvements in the mesh phantoms, such as inclusion of blood content and anatomical modifications of certain organs, which change the distance between the organs. In addition, the inclusion of cortical bone also contributed to the differences. We found very large differences when the thyroid is the source and the ET region is the target, with assays differing by up to 170 times at low energies. The differences were even greater for electron SAFs, with the largest differences reaching up to 1,600 times. This slide shows an example of electron SAF for elementary tract organs, comparing the left column results between the mesh and satellite models. When either the mucosa or content were the source region, the mesh phantoms provided much higher SAFs for the entire energy range. This is mainly because the target region mass in the stylized model was significantly overestimated compared to the mesh phantom. In fact, the observed fractions themselves were quite similar. The differences were even greater when the content were the source region, because the stylized model contained a much larger content volume than the mesh phantoms, which resulted in more particles to be observed within the content. And considering the mesh phantoms reflect realistic anatomy and at the same time match all the ICRP reference values, we believe that they provide more reliable results. Finally, this slide shows an example of electron SAFs for the respiratory organs, comparing the small BB region. Again, the mesh phantoms showed much higher SAFs than the stylized model, and the maximum difference was the 5 times. These differences are also mainly due to the much smaller target mass in the mesh phantoms. In addition, the airways in the mesh phantoms showed some crossfire effect between the branches, which further contributed to the differences. Finally, here is a summary of this talk. ICRP publication 156 introduced the development of new pediatric mesh-type reference computational phantoms converted from the voxel phantoms with the anatomical improvement. The developed phantoms preserve the original topology of most organs of the voxel phantoms, includes the detailed and more accurate models for several organs, includes intra-organ blood content, and also micron-thick target and source layers in the skin, urinary bladder, and elementary and respiratory tract organs. The developed phantoms can be directly used in the general-purpose Monte Carlo codes, such as GM4, Fitch, and MCP6, and provide comparative computation speed compared to the voxel phantoms, except for the MCP6. The pediatric mesh phantoms provide similar dose values for highly penetrating radiations, but more accurate and reliable dose values for the weakly penetrating radiations. The developed phantoms will be used in all other future calculations of ICRP radiation protection system and also provide valuable research for wider use in the radiation protection applications. Thank you very much for your attention.
Thank you for attending the ICRP Publication 156 webinar. My name is Bang Shin, a member of Task Group 103. Through this webinar, I will introduce how to download and use the pediatric MLCPs. The ICRP provides pediatric MLCPs and their corresponding Monte Carlo code examples as the supplemental electronic files with Publication 156. This presentation will cover a detailed description on these files. First, you could download the supplemental data files via Publication 156 website. The file contains two folders, Phantom Data and MC Examples. Then, let's start with the Phantom Data folder. This folder contains the files related to phantoms such as tetrahedral mesh and polygonal mesh files, the media, bone, blood, and 3D PDF files. First, the polygonal mesh phantoms are provided in the OBJ file format. In this webinar, we will skip the description on the OBJ file as it is widely used file type. As already mentioned in the previous presentation, the tetrahedral mesh phantoms can be generated by filling the polygonal mesh phantoms with the tetrahedrons via tetrahedralization process using the TETGen or Poly2TET software. As you already know, the tetrahedron can be defined by 4 vertices and 4 faces. The node file contains the vertex information and the L file contains the node information. With the 4 vertices read from the node file, the L file automatically constructs 4 faces with the following sequence. For the node file, the first number in the first line shows the total number of nodes comprising the phantom. From the second line, the first number is the node ID and the following 3 numbers are the locations in X, Y, and Z dimension. For the L file, the first number in the first line shows the total number of tetrahedrons comprising the phantom. The next 2 numbers respectively means the 4 nodes comprising the tetrahedron and the organ ID. From the second line, the first number is the tetrahedron ID and the following 4 numbers are the nodes comprising the tetrahedron. And the final number is the organ ID. The media file contains the elemental compositions and densities of each organ. The sum of the elemental composition is unity. The first number is the medium, and through this medium number and table 8.2 in Annex A, the users can match the physical property of each organ and tissues for those calculations. For example, the medium for the adrenals are 1, and those for ET whorls are 2. The blood file contains the fraction of blood in each organ. The first column shows the medium number and the second column shows the ratio. For example, you can see from the first line that the medium is 1 and ratio is 0.167. This means that the 16.7% of the adrenal is blood. The next is the bone file. For the pediatric MRCPs, the bones consist of 3 regions, the cortical bone, spongiosa, and medullary cavity, which are the homogeneous mixtures of red bone marrow, yellow bone marrow, trabecular bone, cortical bone, and miscellaneous skeletal tissues. The bone file contains the fraction of bone tissues in each region for each bone site. For example, if you see the blood exclusive ratios for the upper humerate cortical bone, which is the first line here, you can see that the values for the cortical bone is 0.926 and the miscellaneous skeletal tissue is 0.074. This means that if you consider the parenchymal tissue mass fraction of the upper humerate cortical bone, it comprises 92.6% of cortical bone and 7.4% of miscellaneous tissue, and there's no red bone marrow, yellow bone marrow, and trabecular bone. Finally, the folder contains the 3D PDF file. The users can use this file to easily visualize the MRCPs in the polygonal mesh format using the Adobe Acrobat software. The users can rotate the phantoms using their mouse, or they can turn on and turn off the organs in their preferences. So, until now, we explored the phantom data files, and from now on, let's talk about the example codes for the FEATS, MCMP6, and JANT4 code, which provides the implementation of tetrahedral mesh geometry. Each folder contains the external, internal, and phantoms folder. External folder contains the input file for the external exposures, and the internal folder contains those for internal exposures. And the phantoms folder contains the files related to phantoms. There are two simple exposure scenarios, one for external exposure for point source isotropically emitting 1 megaelectron photons located 1 meter in front of the phantom center. And then, the internal exposures for homogeneous liver source isotropically emitting 1 megaelectron photons also exist. For both cases, the average absorbed doses are calculated for each organ. The first code is the FEATS code. The FEATS example comprises 6 sections: the parameters, source, material, surface, cell, and T-deposit. Let's start with the parameter section first. The parameter section covers basic FEATS settings such as calculation mode, number of primary particles, physics model, and the other option. The ICNTL parameter in line 9 is on the calculation mode. When this parameter is set to 0, FEATS is run in the normal calculation mode. The next two lines are regarding the number of primary particles. The max cast is the number of histories per batch, and the max batch is the number of batches. This means that the number of primary particles can be calculated by multiplying max cast by max batch. The NEGS parameter in line 19 is to decide whether the EGS5 mode will be used or not. When NEGS parameter is set to 1, the EGS5 mode is used to transport photons, electrons, and positrons. The next parameter is file parameters in line 17 and 18. These parameters are to specify the physics library. You can set these parameters depending on which version you use. Before FEATS version 3.00, manual FEATS cross-section data setting was required. In file 7 parameter in line 17, you should write the path to xsdir.jnd file. And in file 20 parameter in line 18, you should write the path to EGS folder. On the other hand, from FEATS version 3.00, instead of using the file 7 and file 20 parameters, all you need to do is to use the file 1 parameter. In this parameter, once you just write the FEATS installation folder path, the cross-section data is automatically set when running the simulation. And actually, for the recent version, if you install the FEATS in the default installation folder path, you even do not need to write the file 1 parameter to set the cross-section data. Then, let's see how we can implement the phantoms. Before defining the geometry, the materials should be defined in the material section. In the material section, you can find the infl command in line 38, which allows FEATS to read the external files to prevent the FEATS main input file to be very long. The material file can be found in the phantoms folder. From line 3, you can see the material command Inside the square bracket, you can specify the material number. In this example, the material number was set as equal to the organ ID. Then, from line 4 to 8, you can see the elemental compositions and their fractions. The materials are defined for all the organ IDs for the same sequences. After defining the materials, you need to define surface. In the surface section, first, the phantom box was made to fill the box with the pediatric MRCPs. Then, a slightly larger than the phantom box was made, which will be used as universe to implement the phantom. Finally, the world boundary box was made to transport the particles only in the regions of interest for effective simulation. In the cell section, the geometries are constructed in the main space. In the cell file in line 2, you can see that the lattice equals to 3. When you set lattice equals to 3, the tetrahedrons are implemented in the feature code. You can also see that the phantom is specified through tfile parameter with the file path. In line 3, you can also see that the fills equals to 15,000, which is equivalent to the universe number in line 2. This means that the cell 2 is filled with the phantoms. The organs are defined from line 7. The first column is the cell number, followed by the material number, density, surface number, and universe number. In this example, the universe and cell number was all set to the organ ID. After the phantom implementation, the source is defined in the source section. The first is the external point source. In this example, the cylindrical source was used to define the point source. In line 24, the S-type command is set to 1 with the radius and height of zeros. The dir command in line 32 was set to all to generate isotropic source. The next is the internal liver source. In feature code, there are two ways to define the internal source organ. First method is the rejection method. In this example, S-type is set to 2, which is the rectangular solid source. Then, the bounding box for the liver is specified from lines 27 to 32, and finally, the organ ID of the liver, which is 9500, is specified using region parameters in line 38. From feature version 3.02, the tetra mesh source is also possible by setting the S-type to 24. In this way, you don't need to make the boundary box like the first method. All you need to do is to set the source organ ID in the tetreg command. The feature will uniformly generate the source particles in the organs. Finally, the T-deposit section was used to calculate the organ doses. T-deposit section calculates the energy deposition in the interested region. For the tetrahedral mesh geometry, you can set the mesh command to reg in line 54. In line 55, you can specify the organs for those calculations. If you type all, energy deposition will be calculated for all the cell regions. If you are interested in only the specific organ, you can also type the cell number. If you want to calculate the energy deposition for the several organs together, you can type several organ IDs in the parentheses. This is the end of the explanation on the feature code, and additionally, this slide provides a tip for reducing the phantom implementation time in feature code. The MRCPs comprise several millions of tetrahedra, and due to the large number of tetrahedra, feature requires some implementation time. And the implementation time can be reduced by generating the phantoms in the binary format. For this, the itetra parameter in the parameter section can be used. If you want to use the phantoms in the binary file, first, you need to set the itetra command to 2. If you run the feature code, you can see that the binary file phantom is generated. Then, all you need to do is to set the itetra command to 1. Then, you can see that the simulation begins with short implementation time. The default binary file name is tetra.bin. From which version 3.35, you could also specify its name and location via file.dirty parameter in the parameter section. When checked with Fitch version 3.32 with i7 14th generation CPU of Intel, the implementation time was reduced from 4 minutes with element and node files to less than a minute with binary file. So, here's a demo video to run the fetch example in the Linux system. The external exposure scenario was run using the fetch version 3.32. First, if you just open the input file, you need to set the file1 parameter to the fetch installation folder. And then, if you want to use the binary file of the Phantom, you can change the itetra into 2. Then, if you run the fetch simulation, you can see that the tetra.bin file is generated. Then, what you need to do is to open the input file and change the itetra parameter from 2 to 1. And then, run the simulation. As you can see, following the maxcast and maxbatch parameters, you can see the simulation is running. Once the simulation is done, you can just open the result file and see the dose values. This is the end of the fetch code explanation, and the next code is MCMP6. The MCMP6 input file comprises cell card, surface card, and data card. To implement the phantoms, first, the materials for each organ was defined in the data card. In the data card, you can find the read file card in line 45, which allows MCMP6 to read the external file to prevent the main input file to be very long. The material file can be found in the phantoms folder. From line 3, you can see the material information. Right after the alphabet M, you can specify the material number. Then, from lines 4 to 8, you can see the elemental compositions and their corresponding fractions. Following this format, the materials are defined for all the organ IDs. Then, the surfaces were defined to construct the geometry. In the surface card, the phantom box is defined in line 24, and the word box is defined in line 25. In the cell card, the geometries are constructed. The cell information is in the cell file in the phantoms folder. The first column is the cell number, which is followed by the material number and density. Then, you need to specify 0 right after the density to classify that these cells are the pseudo cells, which means that these are the universe belongs to the phantoms. After pseudo cell notation, you can add universe to define the organs. In this example, the universe was set to 2. In the last line, you can also see that the background material is additionally defined, which is not defined in the phantoms. The background means that the region that is inside the phantom box, but is not occupied by the phantom, like the blue region in this figure. In this example, cell 15,000 was added with the void material. Once the cell file is read, then, in line 17 of the main input file, the phantom fills the phantom box using the fill card. Finally, the word is defined in lines 18 and 19. So, we finished to define the surface and cell cards for geometry definition. Someone might have already noticed that we did not set the phantom file yet. Then, how can we implement the phantoms? To specify the phantom, the embed card should be used in the data card. Right after embed in line 48, you should write the phantom universe number, which is 2 in this example. Then, set the mesh geometry type using the mesh geo card in line 48. Finally, set the phantom file path using the mesh geo in card in line 49. For this example, by default, the tetrahedral mesh phantom in Abacus file format is used. Through the webinar, we mentioned that the MLCPs are in the element and node files format. However, MCMP6 code does not provide the implementation of these file formats. Therefore, to use the MCMP6 code, you can use the TET2 MCMP code to convert these files into Abacus file. The detailed information can be found in the journal article TET2 MCMP. Coming back to the embed card, you need to define the background cell via line 50, which is 15,000 in this example. And finally, although we wrote material numbers in the cell card, the material should be again defined in the embed card using met cell card in line 51 to apply them to the pseudocell. The material should be defined by typing the integer pairs for each organ. The first number of the integer pair is the embedded pseudocell number, and this number must be sequential starting at 1. The second number of the integer pair is the pseudocell number, which is equal to the organ ID in this example. The next is the source definition. For the external exposure, the particle, energy, and positions are defined in the SDEF card. By default, the direction is automatically set to isotropic direction. Unlike the external exposure, for the internal exposure, special method is required. Unfortunately, the rejection method using the cell in this SDF card does not work for the tetrahedral mesh phantoms. The source organs must be defined in the abacus file, and for this, first, to tell the MCMP that the source is from the abacus file, you should add pos equal volumer in the SDEF card. Then, in the abacus file, you should add set source at the LSET part of the source organ with the number of tetrahedrons comprising source organ. And finally, the tally card is defined in the data card to save the energy deposition in each organ. As you can see from the tally file in the phantoms folder, this example uses F6 energy deposition tallies to calculate doses to each organ. If you want to calculate the energy deposition for the several organs together, as you can see from the below, you can type several organ IDs in the parentheses. And like the feature code, this slide shows a tip for reducing the phantom implementation time. Again, the MRCPs comprise several millions of tetrahedra, and which requires long implementation time. Until MCMP version 6.2, about half a day was required to implement the MRCPs, which is very long. From version 6.3, the implementation time has significantly improved, but still requires about half an hour. From MCMP version 6.2, you can significantly reduce the implementation time using the MCMP file. For this, you can use the convert utility to convert the abacus file to the MCMP file. The convert utility is automatically installed if you install the MCMP version 6.2 or higher. You can generate MCMP file by running the convert utility with -a option to input the abacus file and -um option to output file. From version 6.3, MCMP newly introduced the HDF5 format. Although the HDF5 requires same amount of implementation time with the abacus file, it facilitates the visualization of the phantoms by implementing them in the software such as Purview. If you want to use MCMP or HDF5, all you need to do is to change the abacus in line 48 to the MCMP or HDF5. And then all you need to do is to change the file name in line 49 in accordance with the new file name. As you can see, if you use the MCMP file format, the implementation time takes less than a minute for Intel i7 14th generation CPU. So here's a demo video to run the MCMP6 example in the Linux system. The external exposure scenario was run using the MCMP 6.2. In this example, I have already converted the abacus file into MCMP file. If you want to use this MCMP file, you need to open the input file and go to the data card. And in the data card, in the mesh.geo card, you have to change the abacus into MCMP and change the phantom name in mesh.geo in card. Then, all you need to do is to run the MCMP simulations. Then, you can see that the MCMP file is read here. then simulation begins within very short time. After the simulation, you can see that the M, O, and R file is generated, and if you open the M file, you can see those results. So this is the end of the MCMP6 code, and the next code is JANT4. In this example, you can implement the MRCPs using the TET model import, TET detector construction, and TET parameterization classes. The TET model import class is to import the phantom data such as element, node, and materials. In JANT4, all the geometries are constructed in the detector construction class. In this class, the tetrahedral mesh phantom is defined by TET parameterization class in this example. When you run the JANT4 code, the TET model import class imports the element and node files using the data read function and the material file through the material read function. After the data read, in the TET detector construction class, the world boundary and the phantom box are defined. Also, the parameterization class was used to fill the phantom box with the tetrahedrons in the detector construction. The tetrahedrons are installed in the phantom box using the compute solid function of the TET parameterization class. And the materials are applied to each tetrahedron via compute material function. Until now, we talked about the installation of phantom geometry. Then, from now on, we will talk about how we can calculate organ doses. In detector construction, in addition to the geometry, the scorer can also be constructed. In this example, we use TET PS energy deposit class to save the energy deposition in each organ, and the saved energy deposition is then gathered in the TET run class, which is finally printed out in the TET run action class. In the TET detector construction class, this example constructed the sensitive detector using the TET energy deposit class. During the particle transportation in the TET PS energy deposit class, every time a step loses its energy, the energy is deposited in the organs. Then, the saved energy deposition are gathered in the TET run class. Once the simulation is finished, the dose values are printed out and saved as a result file via the TET run action class. In the result file, the users can find the number of primary particles, organ ID number, organ mass, dose values, and statistical relative errors. The next step is how to set the source particles. The TET primary generator action class is used to generate the source particles, and for the external exposure scenario, the source particles are generated through the G4 general particle source class. And for the internal exposures, the source particles are generated via G4 particle gun class. For both the cases, a separate source definition file called source.meg is used to generate the source particles. For the external exposure scenarios, the particle direction, energy, type, geometry, and position can be set in the source file. For the internal exposure scenario, only the particle type and energy is specified. Then, what about the source organs? The source organ is defined in the command line when executing the code. Finally, you can find the input macro file in each external and internal folder. In the macro file, you can set the number of CPU threads for multi-threaded mode. Also, you can set the source definition file and the number of primary particles. For JANT4 simulation, this example used CMake to compile the JANT4 code in the Linux system. First, move your directory to external or internal folder, and then make the folder to compile the code. Move to the generated folder and compile the code by typing cmake space ... and then make. Then you can see that the JANT4 code is successfully compiled here, and the execution file named external or internal is created in each folder. Once you successfully compile the code, you can run the simulation by typing the necessary command. For the external exposure, you can specify the macro file after -m command and output file after -o command. by default, the newborn MRCP is implemented in the code. If you want to implement the adult MRCP, you need to additionally type phantom name after -p command. For the internal exposure, basically the command line is same with the external exposure case, except for the command for specifying the source organ. Previously, I mentioned that the source organ can be set in the command line, and that's here. You can type the source organ ID after -i command here to specify the source organ. So, here's a demo video to run the JANT4 example. The external exposure scenario was run using the JANT4 version 11.03. You can make the folder for the compile and move to that folder. You can compile the code by typing cmake space ... and then type make. Then you can open the macro file and set the number of threads for the multi-threaded mode. If you run the JANT4 code, you can see that the phantoms you specified are implementing in the code. And then you can see the JANT4 code is running. Once the simulation is done, you can find those results in the output file. The final example is JANT4 long airways. The long airways were developed for the purpose of internal dosimetry. Long airways from generation 2 to 15 were developed in constructed solid geometry format. Due to the differences in the geometry between the CSG and the tetrahedral mesh geometry, the airways cannot be directly defined in one phantom file. Therefore, to install the long airways in the MRCPs, the parallel geometry feature of the JANT4 code was utilized. The phantoms were implemented in the mesh world, while the airways were implemented in the parallel world. In particle transportation, the parallel world overlays the mesh world, which enables us to perform those calculations using two different types of geometry. In the phantoms folder, long diameter, and long bore files additionally exist, which contains the airway information such as location, diameter, and their volume. Since the code structure is almost identical to the JANT4 code already explained, I will skip the code explanation and proceed with how to execute the code. For the external exposure, the execution process is same. You can specify the macro file after -m command, output file after -o command, and phantom file after -p command. If you execute the code, you can see the long airway information as well as the phantom information. For the airway code, only the dose for the airways are printed out in the output file, not all the organ IDs. For the internal exposures, you could additionally find the source files that contains the location of the source particles. If you specify the following source region acronym after -i command, the source particles are generated from the source location file. For example, if you set AI after -i command, the alveolar interstitial region is set to source region. Like the external exposure, only the doses for the airways are printed out in the output file. Until now, we talked about the example Fitch, MCMP, and JANT code of the publication 156 supplementary files. Finally, let's talk about the skeletal dosimetry. As mentioned in explaining the bone file, the skeletal system comprises cortical bone, spongiosa, and medullary cavity, which means that the skeletal target tissue such as red bone marrow and endosteum are not explicitly defined in the phantoms. Therefore, special consideration is required to calculate doses to these skeletal target tissues. There are two most widely used approximation techniques. The first method is the mass fraction technique. This method computes the doses to the red bone marrow and endosteum based on the doses to the spongiosa and medullary cavity as surrogates. The doses can be calculated by multiplying the site-specific spongiosa or medullary cavity doses by the site-specific tissue mass fractions. This mass fraction can be directly applied with the supplementary Monte Carlo code examples. All you need to do is to just do the post-processing. For the general exposure cases, this method provides reliable dose values. However, when the charged particle equilibrium is not satisfied across the bone site, like the case when exposed to low energy photons, this approximation technique can provide unreliable dose values. Therefore, the advanced approximation technique called fluence dose to response functions, the DRF, was introduced. The DRF exists as a function of energies, and you can calculate the dose values by multiplying the fluences of the uncharged particles with the corresponding DRFs. Then, by adopting the mass fraction approximation technique here, you can calculate the doses to skeletal target tissues. The photon DRF for pediatric phantoms can be found in the electronic files of publication 155. Then, how can you apply the DRF method to the Monte Carlo code? You can use T-track and multiplier sections for Fitch code, F-Otelli and DEDF code for MCMB6, and G4V primitive quarter for JANT4. Although the DRFs are not included in the supplemental files of publication 156, to facilitate your application, the Hanyang University research team additionally provides the input examples for the DRF. You can download the examples through Mesh Phantom homepage. If you go to Monte Carlo Code Input panel, you can download the input examples for the photon DRFs here. And if you also have any questions in using the MLCPs, you can visit the Q&A session and ask. Through this webinar, we explored the phantom structures and Monte Carlo input examples. We hope this webinar is informative for using the phantoms for your future application. And if you have any additional questions in using the phantoms, please feel free to contact us anytime. Thank you.